So one of the last functional groups to talk about now is amines. So we'll start with the nomenclature and properties as usual. So amines are generally considered to be the derivatives of ammonia, which is NH3. And what we do is that we substitute alkyl groups for each of the hydrogens. So you can remove one hydrogen, two, or all the three. So when you remove just one hydrogen, replace it with an alkyl group. It's called a primary amine. A secondary is when you have two alkyl groups. And tertiary is when you have three alkyl groups, so no hydrogens at all. So it's kind of easy way to remember the primary, secondary, tertiary by just having the number of alkyl groups. Now don't forget that the lone pair of electron is still there on the nitrogen, right? So it's part of the bonding, okay, that you have to remember. Okay, so first let's go ahead and do the nomenclature. We're going to try and keep it simple. So we'll do both the nomenclature, even though, that's, you might think not simple, but, both nomenclatures are quite simple. So for the IUPAC, we're going to take the name of the alkane, replace the E with amine, okay? And then for the general name, it's going to be the alkyl group and then the amine, all right? So let's get started. So for the first one, first amine would be only one carbon, so that's methanamine or methylamine, okay? So you can see not very different, you're still ending in the amine. So methanamine would mean that it is IUPAC. Methyl would mean that you're doing the alkyl amine then, okay? All right, so ethanamine, propanamine, and so on and so forth, you can go on, all right? So when you have primary amines, when you have long chains in the primary amines, then you have to kind of name the long chain and also give the locant. So here this one would be 2-propanamine, or this could be called isopropylamine. So the isopropyl group is right there, and then the amine, okay? If it is not something that you can name using an alkyl group, then just give 2-heptanamine, so count the number of carbons, the long chain, and then give the location of the amine group, okay? So 2-heptanamine, this is cyclohexane amine, all right? So keep it simple. Secondary amine and tertiary amines. Now in these cases, you're going to have more alkyl groups in there. So you still have to find the longest chain, okay? And again, there are going to be two nomenclatures here, the IUPAC and the general nomenclature. For IUPAC, you have to find the longest chain. For general nomenclature, you can just use the alkyl groups, okay, as you can see. So here, for example, when you have two methyl groups on the nitrogen, that's a secondary amine. So now you have to find the base name. So the base name would be the longest carbon chain, and here both of them are the same, so it doesn't matter. So here we say methanamine is the base name, but then on the other, to name the other alkyl group, you have to say N-methyl methanamine, okay? So one group then becomes like a substituent, the other is the base, okay? And the base name or the long chain is going to be the longest number of carbons, okay, that you have. Now the easy one is the general name, which is dimethylamine, dimethyl and then amine, okay? All right, so here if you have an ethyl group and a methyl group, so ethyl methylamine, that's the easy way. Now for the IUPAC name, you have to give the long chain, the base name, so that's ethanamine, and then N-methyl ethanamine, okay? That's how it goes. So now you kind of know where we are going with this, okay? So if you are kind of in a hurry and you don't want to name it an IUPAC, then you can just use the substituents, okay? So methyl and then propylamine, methyl propylamine, or N-methyl and then propanamine. That would be the IUPAC. Okay, so that's kind of how it goes. And then if you have substituents also on there, like branching going on, it gets a little complicated. So here you have to then start numbering the long chain. So 1, 2, 3, that's the long chain. So that's propanamine. And then on the second carbon, there is actually this should be 1-methyl. So I'll change that as soon as I get time. So then that's 1-methyl, and then N-methyl propanamine. Okay, and so on the N, on the nitrogen, you have the methyl group. Okay, so 1-methyl N-methyl propanamine. Okay, and here we go with the N-propyl cyclohexanamine. So here is the cyclohexane group that's going to get the base name, the longer or the larger number of carbons here, and so on. Okay. For the tertiary, where you have 3 groups, the easy way is the trimethylamine here, but then the IUPAC name would be, then you have the 3 CH3s. One of them gets the base name, which is the methanamine, and then they have the 2 methyl groups, and so that's NN dimethyl methanamine. Okay, so here if you have 3 different groups on it, find the longest chain, that's going to be your base name, that's propanamine, and then N-ethyl, N-methyl propanamine. Okay, remember the dashes. Okay, so if you have 2 N's, that's a comma. If you have a dash, if you have a letter and another letter, that's a dash then. Okay, and so that's how it goes. Again, keep it alphabetical here. Okay, with the N-ethyl and methyl. More substituents over here. So amine groups actually have no priority whatsoever. Okay, it's just like any other alkyl group. So it's, even though we're studying it last, it actually has no priority for nomenclature. So here if you had a carboxylic acid, that gets priority. If you have an alcohol, alcohol gets priority. So you know, keep that in mind. All right, if you have groups like these, then the best way to do is wherever you have more branching is we're going to start numbering. Okay, so 3-amino, 2-chloro, and then the methyl group over here. Okay, so just kind of keep it that way. No priority whatsoever. And the NH2 group is called the amino group then. Just make sure to keep things alphabetical. When you have aromatic compounds, so you've learned about aniline already, an aromatic compound, so that's called aniline. If you have other substituents on it, then this is going to be N-methyl aniline, okay? And then here you have a CH2 in between the benzene and the nitrogen, so that's benzyl. So that's benzylamine, and then N-methyl benzylamine. Okay, that's how it goes. Any other group on it, you can decide how you want to name this. So for example, here you can give the base name for chlorine, or you can give the base name for nitrogen. And so here I've chosen aniline as my base name. If you wanted to give chlorobenzene, that's fine too. This would be the amino group. Okay, so orthochloroaniline. Here, since you have an aldehyde, it is much easier to name the ring as benzaldehyde and then say, you know, where your amine group is, which is meta position, okay, over here. And here, this one, aniline N-phenylaniline, okay, so any one of the rings is going to be the N-phenyl. You can also have nitrogens within the ring. Okay, so primary amines don't exist in a ring, but as soon as you have a secondary amine, now that can exist in a ring. It can be an internal group. Okay, and so here I've given you a whole bunch of heterocyclics. Now, do you have to know all of them? No, you don't. It's okay. Some of these you will encounter when you get to biochemistry, you know, things like indole and all-imidazole. You will encounter those in biochemistry. And for us, really, we stick to pyrrole and pyridine. Pyridine is a common base and solvent that we use in organic, and pyrrole is a starting material for a lot of things. So, you know, but here, just a list for you for the heterocyclics. Now, amines can also be chiral. Okay, now remember what is chirality. Chirality is when you have an sp3 atom with 4 different groups. Okay, so sp3 is nitrogen also in ammonia. Okay, and so ammonia has no chirality because there are 3 hydrogen groups. So as soon as you have 4 different groups on it, on nitrogen, then it can be chiral. So what happens is that the lone pair of electron is also considered to be a group. So here you have an ethyl group, a propyl group, and a hydrogen. So 3 different groups, and then the 4th one is the lone pair of electron. So which means that this nitrogen actually is a chiral nitrogen. It can have mirror images and enantiomers with all the properties. The problem with some of these chiralities is that because there is a lone pair of electron, this kind of a nitrogen, remember this is trigonal pyramidal. This is kind of like an umbrella. So it keeps flipping on either side because the lone pair of electron, there is no atom, right? It's just a lone pair of electrons. So because of that, it kind of behaves like an umbrella and it keeps flipping depending on where the air is, okay, or where the wind is blowing. And so, which means that the chirality is not steady, which means that it keeps going from one enantiomer to another. So if you want to make an amine a chiral amine, you literally have to remove the lone pair and give it a 4th group, okay, which is something we're going to talk about in a few minutes. But I just wanted you to let I wanted to let you know that amines can be chiral because they are sp3 and they can have 4 groups on them. Okay, I don't know what I have there. I think I was going to say, but there are 4 different groups. Okay, but that's coming in the future, so I'm going to have to, I'll delete that. Okay, so now let's talk a little bit about the basicity of amines. Basicity of amines comes from the fact that there is nitrogen and nitrogen has the lone pair of electrons. So this becomes a very good Lewis base. Okay, it gives electrons. So it's a good Lewis base. So here is the acid HCl, here is a base, and there's what you end up forming. So you don't form salt plus water because there is no traditional hydroxide here. Okay, so this is not, Bronsted-Lowry. This is, it's a Bronsted-Lowry acid, but, this is a Lewis base. So because of that, there is no water. Okay, however, you do get a salt, and see what happened to nitrogen. So nitrogen here now is going to be called an ammonium salt. So in case you're wondering what happened to the chlorine, it is still there, and it will be the counter ion, okay, for the ammonium salt. So it's all there all together. Okay, and so amines are actually pretty good salts because we know ammonia is also a very good, sorry, not salt, a base, because ammonia is also a good base. All right, so as then you start adding alkyl groups on the amine, they start becoming stronger and stronger bases. Okay, so amines are generally even stronger than alcohols or water, and that's because of the lone pair of electrons. Okay, so here you can see how the basicity increases, okay, when you have alkyl groups on it. Remember the pKa, if it increases, then it's a stronger base. Okay, if it's a lower pKa, it's a stronger acid. So here, the more alkyl groups you push, the more electrons you push into the nitrogen through inductive effect. Okay, that's what's going on. Now, there is a little bit of a difference between aqueous phase and gas phase, okay, because of how the structure is for ammonia or for nitrogen. But in a normal kind of a setting where you have gas phase, then a tertiary amine would be the strongest one. Okay, but in aqueous phase, things are a little bit different. And why? Because of hydrogen bonding also. Okay, so don't worry about that. I probably will not ask you anything about aqueous phase. I will ask you, if I ask you about bases, I am assuming that everything is in gas phase or everything is without water. Okay, because I mean, we have to talk about solubility of amines in water also, but the thing is that, yeah, if they're going to have hydrogen bonding with water, then they're not going to be as normal bases, okay, anymore. So when we talk about basicity, please just remove the water component from there. So you don't have to memorize this. Think of these in gas phases and then know that tertiary is going to be stronger than, so let me write that here, tertiary stronger than secondary, than primary, and this is all going to be in gas phase, okay, or without water if you want to think like that. Okay, so keep it that way. Now for the nomenclature for quaternary salts, okay, because when you form a salt, like from acid-base reaction, then of course you form, you form a quaternary amine, and a quaternary amine meaning that you have four things on it. Now quaternary amine means it's a quaternary salt, because by default, if you have four bonds on nitrogen, it gets a formal charge of +1. Okay, so this is going to be a quaternary salt. Now, generally, these are all called ammonium salts, but the ammonium salts will always have a counter ion. So I have the chloride here for you, but generally they will have a counter ion one way or another because ammonia, the nitrogen there, has a +1 charge, okay, formal charge. Generally, I don't go into the nomenclature so much, but I just want you to know these are called ammonium salts, and I gave you some examples, okay, if you want to look at, but otherwise, generally, I just need you to know that these are quaternary salts. Now, in this case, by the way, before I move on, now we have a chiral center, a proper chiral center, because there is no lone pair of electron here. So quaternary salts actually are very good chiral agents, okay, because if you have four groups on them, now there is no flip-flopping around, okay. Now the nitrogen is stuck as it is, so it will have chiral centers, it will have enantiomers, and it will not be flipping flopping around, okay, to do anything. Okay, so let's talk about the basicity. Since we were doing acids and bases, everything is kind of connected, right? So you keep going back and forth, chirality and quaternary salts. But anyhow, okay, so let's talk about the basicity of amines. So one, I already talked about the fact that if you have more alkyl groups on nitrogen, then you're going to have more inductive effect, okay? And so the bases will be stronger the more alkyl groups you have. But when you have an aryl amine, which is an aromatic amine, okay, so if you have an aromatic amine, things are a little bit different because now the lone pair of electrons on nitrogen are actually involved in resonance. So which means the lone pair of electrons are not available for reaction, because remember again, ammonia and all the amines are going to be Lewis bases. If something is a Lewis base, it should be capable of giving a lone pair of electron. And if that lone pair of electron is involved in resonance, well, that's not going to be a strong base then. So it's not as strong as the aliphatic, okay, bases, but aromatic amines are still amines, they're still bases. So it just depends, okay, what kind of, substituents also you have, and amines, they can be still bases, not that they're not going to react as a base. So you can change the basicity of aniline if you add groups or remove, or have groups that are electron donating or electron withdrawing, okay. So for example, here if you look at this one in which you have an aniline with a methyl group, now here the pKa is higher than aniline, okay, because this is methyl group is an electron donating group. So the electron donating group makes the nitrogen a little bit more electron rich, okay. It's not that the resonance is not going on, it is still going on, it is just that it's more electron rich. Compare that to something with chlorine, compare that to nitro group which has such a low pKa, all right, because now electrons are being withdrawn from the benzene ring, okay. So you can change the basicity of aromatic amines, well, even aliphatic amines, the same thing, okay. The more you make the lone pair of electron available for reaction, the stronger the base is going to be, okay. That's all you have to think about. Am I giving it more electrons? Am I removing electrons from whatever compound I have, okay, with the nitrogen on it? Okay, and little bit some more examples over here, because when you have something which aromatic compared to non-aromatic, look at the difference in the pKa, and that's because again resonance. Okay, so nitrogen electrons here in the aniline, they were involved in the resonance with the benzene, whereas in this case the amino group is by itself, no resonance, and therefore the electrons are able to react as a base, and so the pK is pretty high for this. Okay, the same thing happens with heterocyclics. Now we've talked about this way before, so we'll just kind of review it here, is when the electrons are available or not available for resonance. Okay, and so aromaticity is a big force, okay, for any kind of stability. So for example, if you look at pyridine, the nitrogen electrons here do not have to be involved with benzene resonance, because here the I should say the 5-membered ring here, or 6-membered ring, heterocyclic ring, already has resonance, okay, and already has the Huckel's number. So it already is aromatic. It does not need electrons from nitrogen. Now, in this case where we have imidazole, in the case of imidazole, you can see there are two different kinds of nitrogens, okay? And the two different kinds of nitrogen, in which here there is a lone pair of electron. Well, there is lone pair of electron here also, but this lone pair of electron is actually involved with resonance, okay? And that makes it aromatic. So, which means that these nitrogen electrons are involved in aromaticity, but these electrons are not involved in aromaticity. So what does that mean? It means these electrons are available for reaction. Okay, so just like over here also, this nitrogen electrons are available for reaction. In case of imidazole, here, let me clean that up. In the case of imidazole, you have one nitrogen available, but one nitrogen not available for reaction. Okay, so this is something that you have to keep in mind when you're looking at the basicity of nitrogens. Okay, especially when you have heterocyclic rings, then you have to think about, is it involved in resonance or is it not involved in resonance? Okay, and so you determine from there if it's going to be basic or not, the nitrogen. Some of the physical properties of amines, so boiling points, yeah, depending on how many hydrogens there are, the boiling point will be higher for primary and of course lower for tertiary, because there is more hydrogen bonding in case of primary amines, okay? And so then again with the molecular weight, definitely that's there, higher the molecular weight, higher the boiling point, okay? So keep those things in mind. Solubility in water is also more like that. If you have primary amine, it's going to be more soluble, secondary less, and then tertiary is not going to be soluble. So keep those things in mind as well. Primary, secondary, tertiary, I mean. And then odor, oh my God, amines are actually terrible smelling. They are just bad smelling, okay, compounds. So here are some examples. So the fish smell is trimethylamine. Cadaverine putrescine just tells you, okay, like these are bad smelling things, okay. Cadaver is a dead body, and putrescine just means something that's putrid and it's just been decaying for a while. And these are diamines, okay. So I mean, odor is just bad. You find a lot of amines in nature, okay? And I've been talking about all these functional groups and all the functional groups that occur in nature, which all of them do, a lot of them do actually, and amines is no less, okay? It's almost as common as, I would say, carboxylic acids, okay, in there. And alcohols for that matter. So here you have amino acids, okay, which have an amine group. So we talked about this in carboxylic acids also. And now we come back here again with amine. So there are 20 amino acids, 10 essential, 10 non-essential. So that's an important thing for us as far as we are concerned, because proteins are made of amino acids. And if we don't have proteins, we don't have a lot of things in our body then, okay? And so that's important for us. Then here we have the nuclear bases, and nuclear bases make up the DNA and RNA. Okay, they're the backbone. It's not to the backbone, but they are kind of very important as far as making the hydrogen bonding, making the double-stranded DNA and all that. Okay, so it's a really important thing here. So look at all the nuclear bases, adenine, guanine, cytosine, and whatsoever, and then you can see all the heterocyclic rings in there. You have the amine group hanging out also, but you also have a lot of heterocyclic nitrogens. Now, depending on what kind of a ring it is, it might be either aromatic or not. Okay, some nitrogens are available for hydrogen bonding, some of them may not be available for hydrogen bonding. So a lot of things going on here, okay, with the nuclear bases, but you can see the main thing, nitrogens, okay, everywhere. The other most important class of compounds that nitrogens make is neurotransmitters. Okay, and I have a lot more for you in the next one, but acetylcholine is our most common neurotransmitter, and this is the one that gives you that's the chemical that goes between synapses, okay, and transmits the signals from one neuron to another, okay. So it's a really critical thing. So neurotransmitters control a lot of the emotions in our body, okay, and so very, very critical. Here are some of the neurotransmitters. These are also called alkaloids. Alkali meaning bases, so that's nitrogens. Okay, so alkaloids are a whole class of compounds. There are some here that you will recognize. So for example, caffeine. A lot of us are addicted to caffeine, and that's, a neurotransmitter. If you don't have caffeine, then depending on how much you take, you might have withdrawal symptoms. Nicotine, people know for having withdrawal symptoms from not smoking cigarettes. So, these two are the most commonly and legally available drugs, okay, sort of. But these are the neurotransmitters, okay? And then I've given you some more: quinine, choline, strychnine. Here's morphine and codeine. You can see how complicated their structures are, and the heterocyclic rings that are involved here. A lot of these have been synthesized already, but they're complicated structures, okay? They're not all that simple. The only one here, if you can recognize, that is synthetic and does not occur in nature is, you guessed it, I hope, LSD. LSD does not occur in nature. This is a synthetic alkaloid, and this neurotransmitter is really, really bad. Okay, but I mean, there is a whole alkaloids by themselves, a whole class of compounds, and we study them a lot because all the drugs, they all have these kind of groups in them. Okay, and so it's something to be studied. But anyhow. A lot of these are addictive, and we have receptors for these alkaloids. Don't know why we have these, because we certainly don't need caffeine or nicotine or anything, but we do have. One last point I want to make before I move on from this slide is that a lot of these alkaloids are also not, any particular this of these ones, but they're also used by snakes and frogs. So the venom that they actually have alkaloids in them, and when they bite their victim, they paralyze them, and that's a neurotransmitter. Okay, to make an antidote for that particular neurotransmitter, you actually have to get that neurotransmitter. So not every antidote works for everything. So, if one gets a snake bite, the doctor really has to know which snake bit you, because the antidote can be very, very specific. Okay, so there are a lot of people who actually do that as a research, to find out all the alkaloids in snake venom and frogs and spiders and whatnot. But anyway, that's the last thing I wanted to mention here. And then you also find amines and dyes, okay, and dyes are really interesting because they are colored, and so we use dyes a lot for, of course, coloring anything possible, like paint or clothes, paper, everything like that. Okay, so of course indigo, you will know from, if you wear jeans, this is the color, okay, the blue color that you get. So indigo can be synthesized also, but naturally it was first obtained from, yes, you guessed it right, India. Okay, so it says right there, indigo. But all these other dyes, I mean, I've only given a couple here. There are so many more dyes out there, but all of them you will see they have nitrogen groups in them. Okay, and a little bit more you will learn later on as to why dyes are colored, and that's depending on conjugation. Okay, so that's something we do in spectroscopy. So in UV vis spectroscopy, ultraviolet visible spectroscopy, you learn about the fact that why these dyes actually absorb color. Okay, so there's a lot of interconnections there. So I think, yeah, that's all we have. Main thing, please learn the nomenclature, the physical properties, and the basicity, definitely.